To cruise the entire motorway network of Switzerland, you would have to cross 2,235 bridges. Every day, each of these bridges carries thousands of cars and trucks, and the numbers are rising. Accordingly, the wear on materials, mostly reinforced concrete, is substantial and maintenance costly. The Swiss Federal Roads Agency has commissioned researchers to establish new, resistant and cost-effective materials for bridge building. Gabriele Neuhaus witnessed the initial tests. The bridge of the future, as envisaged by a team of researchers from the Swiss Federal Institute of Technology, Lausanne, will be made of glass fiber materials like this, and is bonded together with glue. For years, the prime material used in road building has been reinforced concrete, but there are decisive disadvantages. In contemporary bridge building, iron reinforcements are a weak point. If they get wet, they corrode and become brittle. Reinforced concrete bridges have a high dead load, and assembling the massive slabs for the traffic lanes is demanding. That is why the Swiss Federal Roads Agency is seeking new solutions for bridge construction. It's a fact that in Switzerland, only considering the motorway network, there are 30 to 50 bridges every year that will have to be replaced. On the entire Swiss road network, it will be a multiple of that. Bridge replacement causes great traffic obstructions. Normally, the bridge is kept open while undergoing the work, so project speed is of the essence. In this respect, industrially manufactured lightweight lane segments are of great advantage. They can be mounted rapidly or can be used to build a temporary relief bridge to detour traffic. 20 strain gauges on the steel girder and a total of 74 sensors on the road segments were installed to test the new material. The composite elements are now to be bonded to the steel girder using a two-component adhesive. This is a completely new approach and is to be tested for the first time on an object of this dimension. For optimal bonding of the individual elements, the researchers apply the adhesive with great care and precision. For the pivotal question is, will the adhesive stand up to the load test or not? Time for the first road segment. It is cautiously positioned on the prepared girder. To subsequently ensure valid test results, everything has to be correct to the millimeter. Herbert Girdler is convinced that both material and adhesive process will generate great advantages. Of course, our prime concern is an effective bond. We want to be faster than other joining techniques. Improved durability is also a target. Specifically, we are not subject to corrosion, as is the case for reinforcements within the concrete. We are principally aiming to achieve an effective transfer of forces. Bonding the new synthetic elements to the steel girder and joining them together requires around 50 kilograms of adhesive. To make best use of the glue, the researchers have to work swiftly. The test bridge has a span of 7.5 meters. This amounts to a scale of 1 to 2 for the calculated actual bridge. Upon completion of work, the entire construction is loaded with a steel girder. Prior to the test, the adhesive now has to harden for around 2 weeks. The time has come. In the testing facility of the Swiss Federal Institute of Technology in Lausanne, final preparations for the load test of the bridge model are in progress. The road segments are loaded at 2 points. The technician gradually increases the load up to 220 kilonewton, corresponding to 22 tons. The load-bearing capacity of the bridge is verified. We'll then slowly advance towards rupture, which we anticipate at around 280 kilonewton. That's according to our calculations. As there is very little intelligence on this material, maximum load is only an estimate. Now the head of research, Thomas Keller, has arrived. Suspense is rising, as meanwhile the load is well beyond the targeted 220 kilonewtons. There's a suspicious cracking sound. The load is currently at 280 kilonewtons. For security reasons, Herbert Girdler asks his colleagues to step back. Initial cracks appear, but the test bridge holds up. The load has already reached 346 kilonewtons. There's a distinct curvature, but girder and road segments remain intact. The load increases further. According to calculations, the bridge should have folded long ago. Then there's a bang. The bond finally yields at 410 kilonewtons. Our calculations were not flawed, breakage behavior simply diverged from our expectations, and if we knew exactly when the girder would fail, tests would be unnecessary. Bridge builders still rely on reinforced concrete. As yet, the new material and the adhesive concept still meet with constructors' skepticism. In Lausanne, however, a further test has produced more promising results, and already next year, the first real bridge is to be furnished with synthetic road segments.